Welcome to Module 3, Lesson 1, Generating Equivalent Expressions. And this opening exercise, actually, if you did come into a classroom, I would hand each and every one of you an envelope with some triangles and some quadrilaterals in it. And then we would begin a small group activity. But we're not going to do that. I'm going to just show you what would have been in your envelope because they were all identical, and we'll go from there and we will start working on that opening exercise, and we'll do this together bit by bit. Okay, so first let's see what would have been in your envelope. Actually, I'm not going to show you what was in your envelope because we need to generate some expressions first to determine the possible number of sides that would be in your envelope. Okay, so for example here, let's go ahead and just turn to that opening exercise. So it says each envelope contains, excuse me, each envelope contains a number of triangles and a number of quadrilaterals. Okay, we need to know something about both of those. Hopefully we do. For this exercise, we're going to let T represent the number of triangles and Q represent the number of quadrilaterals. Okay, so we have our variables. We have T and we have Q. Okay, and that is they're going to equal the numbers of quadrilaterals and triangles. Okay, so the first thing, this first part asks you here, this A, again, we haven't opened up our envelope yet, but it asks you now to write an expression using T and Q, okay, using our variables here, that represents the total number of sides in your envelope. Okay, now we don't know how many triangles or quadrilaterals are in there, and that's the point, okay, is that we don't know, but we want to write an expression using T and Q that represents the total number of sides in your envelope, okay? And then explain what the terms in your expression represent. Maybe you have some idea of this right now, and if you want to, I'd like you just to go ahead and pause, because I'd like you to to do this on your own first and check back. So you can go ahead and pause and then come back and we'll do this together. Okay, so if we're going to use T and Q, we need to know a few things about triangles and quadrilaterals, because we are talking about number of sides. Okay, so if we have a triangle has 3 sides. Okay, and of course a quadrilateral has 4 sides. Okay, that is really important. Okay, because we want to know the number of sides. We need to, in the envelope, we need to know the number of sides in a triangle and quadrilateral. I'm not trying to talk down to you here, but just want to make sure that we understand. Okay? So, if we're going to write an expression, we have T, number of triangles, plus Q, number of quadrilaterals. Okay? Now, each T, or each triangle, has 3 sides. Each quadrilateral has 4 sides. Therefore, here is our expression right here. This expression will help us determine the number of sides in the envelope. Okay, so what's wonderful about these expressions and their real-world application is that this very simple expression right here can be applied to anything. So as soon as we open up and we find out how many triangles we have and how many quadrilaterals we have, we will be able to determine very quickly through some multiplication and addition what a number of sides are in that envelope. Okay. Now, if we want to look at, if you had watched the vocabulary, the relevant vocabulary video before this one, we could look at some terms here and look at some definitions. And if you remember, this 3 here and the 4 here are both called coefficients. Okay, just try to keep this vocabulary alive. They're the coefficients, and then we have the t is a variable, and the q is another variable. Okay, so here we have our expression. Our expression is made up of 2 terms. Okay, remember that terminology as well. 2 terms, 3t plus 4q, 2 terms in this. This would be expanded form, and it's also standard form because everything has been combined. And we have 2 coefficients, 3 and 4, and then 2 variables, the t and the q. Okay? All right, so now you would be put together with the next part of this, this problem here, this opening exercise. You and your partner have the same number of triangles and quadrilaterals in your envelopes. So everyone in the class would have the same number in their envelope. You'd be working with another partner, okay, and you have the same. All right, this is what you know. Okay, and now, so therefore, now you're going to write an expression that represents the total number of sides you and your partner have. Okay, you and your partner have. Okay, total number of sides in that envelope that you and your partner have. If possible, write more than one expression, and it is possible. Okay, just to let you know, more than one expression to represent this total, and there are a number of ways to represent this total. I would tell you I could think of 3 that are pertinent, okay, or that come right to my mind. One simpler than the next, okay. So yeah, there you go. So just remember, here's what you have. Here's what you have. This is what you have done to represent the number of sides in your envelope. So if you can, right now, go ahead and pause and create an expression down here in B to represent the number of sides you and a partner would have in your envelopes together. Okay, so I'm going to pause here, and then you can do that. Come on back, and we'll check your answer. Okay, so as I mentioned, there were a number of ways to write this up, and I was thinking of 3 ways in particular. The first way, which may have come to you, was simply to put 3t plus 4q plus 3t plus 4q. Okay, I mean, you could have done that because you have this would represent your sides in your envelope, and this would represent your partners. Okay, that would be pretty simply done. You can look at it though and say that well, we know it's expanded form. Okay, we try to get to standard form, try to combine like terms, and that's something we've said before. Combining like terms. In this case, you see you have the like terms here, the 2 t's, and you have some q's. Okay, so if you did do that, combined like terms, that would be the same as or equivalent to 6t plus 8q, an expression now that is in standard form because all like terms have been combined. Okay, so here's a second way. All right, and another way would be to set this up using the distributive property, which would have been, you take the 3t plus the 4q, and then you put a 2 in front of it, which means that I am going to multiply this by 2 because I'm talking about my partner and myself. I'm talking about 2 people, okay? If I were to add, hey, let's say another person joined the group, I could change that 2 to 3. Okay, I could change it to 4 if there were 4 people involved. A real simple way, actually, probably, if you're going to, look into the future, probably a preferable way to set it up initially. But you may have to eventually get it to like terms to make it a lot easier eventually, because what's going to happen is this here is going to turn into that there, okay? It's going to turn into that eventually because you're going to distribute it out. 2 times the 3t equals the 6t, and then 2 times the 4t equals the 8q. 4q equals the 8q, okay? Okay, so part C here says that each envelope in the class contains the same number of triangles and quadrilaterals. So write an expression that represents the total number of sides in the room. And hopefully you would understand how and which piece of information you would need to actually complete this, this expression. And that's this idea of total number. We would need to know the total number of students in our class. Okay, so when everyone shows up, which seems to be a rare phenomenon these days, we have 18 students. Okay, so go ahead and pause if you want right now and write an expression that represents a total number of sides in our entire class. Okay, so hopefully you saw you had 18 students. Okay, telling you that there are a number of ways, and I'm hoping that most of you defaulted to this method. Okay, which I think, like I said, I prefer. I like this very well because it says a lot more than, let's say, if we did the multiplication. This could have been, what, 54t? You could have done this one as well, okay? And it's not that this one is wrong. It wouldn't have been wrong at all, okay? 72q. Okay, you could have done this one right here, okay? But why I like this one here, this one right here, because it says a lot more, actually. First of all, it tells us our general expression for one envelope, which is the 3t plus 4q. So it tells us what's inside of an envelope. Well, not really. It doesn't tell us how many, but it just tells us the general formula or the expression for inside the envelope. And then it tells us we had 18 of those envelopes. Okay, so it gives away a lot more information. And again, if you start here, you're going to eventually get here anyway. So some of you may argue that this might be the best way to start, best place to start. They're both similar. Actually, they're both equivalent. Yeah, let's use the vocabulary we are meant to use here. They are both equivalent, therefore they will yield eventually the same result. Okay, the same result. They'll give us the same answer or solution in the end. Okay. So here's part D. Part D says use the given values of T and Q and your expression from part A to determine the number of sides that should be found in your envelope. Okay, so these given values here, the given values of T and Q, I would just have someone in the class tear open their envelope and find out that it looked like that. Okay, and you can see in each one of those envelopes we would have had 1, 2, 3, 4 triangles and 1, 2 quadrilaterals. Okay, so that's what we have in the envelopes. Okay, so now using those given values, okay, right here we had 4t, and we had, actually I can't do that way. I should just say we had 4t. Well, I guess we could do 4. So 4 triangles and 2 quads. Okay, 2 quads. Okay, so using these given values here, okay, and your expression from part A, we'll go back here, and here's our expression from part A is right here, 3t plus 4q. Okay, so let's remember that, 3t plus 4q. Okay, use those to determine the number of sides that should be found in your envelope. Now, this idea of should is that only one, the idea is in class, one kid has opened it up, the envelope. And what was stated before is that everybody, each envelope in the class has the same number of triangles and quadrilaterals, okay? So, you would just assume whatever that kid has in his or her envelope, you're going to have as well. Okay, so what do you do here? Some of you know you can pause. I'm just going to continue talking. You can pause right now and do it yourself because that's the kind of person I am. I would want to do it myself if I knew how to do it. But I'm just going to continue talking here. Okay, so what we do now is we have our expression right here. Okay, we have our variable set up. Okay, now all we need to do is plug in the values that go with that variable. The t, how many t's do we have? We have 4. Okay, we plug it in. 3 times 4, okay, because that means we had 3 sides. That's our coefficient. 3 sides to every triangle, which was a variable. So we substitute, we actually plug in now the 4 here because it exists over here. We know we have 4 triangles in there, plus 4, which is the coefficient for quadrilaterals because each quadrilateral has 4 sides. Plug in the fact that we have 2 quadrilaterals in our envelope. Okay, and with that plugging in, we just continue, and that's 12 plus 8, which equals 20. Okay, so each of our envelopes, which contain 4 triangles and 2 quadrilaterals, each of those has 20 sides. Okay, 20 sides. Okay, and now part E asks us here to use the same values for T and Q and your expression from part B, okay, now from part B, to determine the number of sides that should be contained in your envelope and your partner's envelope combined. Okay, so if we just go back and we know we have, of course, this is right here, we have 4, again, we have 4 triangles and 2 quadrilaterals. Okay, and now if we go back to part B, and we see we had, you can choose one of these here, I mean, whichever, this one or this one or this one, okay. I'm going to choose myself, I'm going to choose to use this one, which you know I like. Okay, so it's 2, 3t plus 4q. Okay, that's my expression I'm going to choose. But again, you could choose either of these. Okay, either of these expressions here. Okay, you can. All right. So if I go ahead and the way I'm going to determine my number of sides that should be contained in the envelope for both myself and my partner combined, I just plug in again. And I'll go ahead and I'll keep my 2 here, plug in my 4 for my number of 4 for my number of triangles, okay, right there, and then 2 for my number of quadrilaterals, okay, right, and again you can see, hopefully, this 4 is here, this 2 is here, okay, because that's the number of triangles and quadrilaterals I have, right? Now if I continue this, I would have, I'm just going to continue down here, but so 2 times 12 plus 8, and you can see right in there, all of that, you can see what that equals, is 20, right? Because we knew that already from the other one. So 2 times 20, which equals 40, okay? Which just makes good sense, because if we had 20 sides in our one envelope, we are surely going to have 40 sides in our envelope plus our partner's envelope combined. Okay? But the most important part of all of this is being able to use expressions. Use expressions, use the values for your variables, plug those in, and come up with an answer. Okay? And that's what we are doing, and that's what we did here in D and here in E. Okay? I'm going to erase, I'm going to pause right now, erase all of this, and we can do F. Okay, so continuing here with F, use the same values for T and Q, and your expression from part C to determine the number of sides that should be contained in all of the envelopes in the class. Okay, so let's go look at C. We ended up with this expression here, and again, you could choose that expression, you can choose this expression to work with, you can choose another that's equivalent. Okay, those are two equivalent. I'm going to use this one, okay, because we have 18 students in the class. This stays the same, which I like this because this represents one envelope, right, like I had mentioned, and this represents the number of children in the class. I like that it's very clearly representing what we are working on. And again, we have 4 triangles, 2 quadrilaterals. Okay. Again, merely plugging in, same thing. We're going to be doing the same exact thing as we did in E. We are just going to do all of this. I just want to do this again just so we get practice with it, especially those of you who are feeling a little bit shaky now. Okay. And then I continue 18, 12 plus 8. See that, and then 18 times 20, and that will equal, what's that, 100, is that 108? No, oh my gosh, I'm so sorry. That's 100, no, what is that? That's let's see, 360. Yeah, so 360, we'd have 360 sides in our class. That's total, okay? 18 times 20. We have 18 students in the class, 20 sides per envelope equals 360 sides total. Okay? Hopefully that's becoming clearer and clearer. I absolutely love this stuff, and I saw a little excitement in the class yesterday when I mentioned we'd be doing this, equations and expressions. So not a lot of excitement, but a little bit of excitement. You know who you are, you excited one. But I hopefully more of you will share her excitement by the time we're done with this module. Well, the last question, G here, says, what do you notice about the various expressions in parts E and F, and again, I didn't necessarily require that you use different expressions, but I mean it's going to look just like here. What do you notice about these two expressions here? This one and this one. Well, they're equivalent, okay, because they're going to give you the same. They're going to come up with the same value. So if we went ahead and well, let's go ahead and do this one. Let's go ahead and plug this one in right here. So if we did 54t plus, what was the other one? 72q, okay, which was equivalent. This expression was equivalent to this one, okay. This one I like I said, I prefer. But this one is equivalent. So if we use this, and maybe some of you did, we could therefore just go ahead and plug in our values. 54 times 4 plus 72 times 2, which is going to equal, what's that, 216, which is this here, 216 plus is that 144? Okay, that's summoned. What the hell does that word mean? Summoned. Part of the sun. Oh. Okay. What's the mistake? Good drive. That's so strange, huh? Damn it. Yeah, but this is something different, huh? It's a new module. Okay, expressions and equation. No, there's no error. Okay. Damn it! Okay, so moving on to example one. This is kind of our introduction to this idea of any order, any grouping property with addition. And what any order and any grouping refer to, they refer to the two properties that we've talked about already, commutative, okay, and associative. All right, so this idea of commutative means you can move things around, so you have any grouping, associative, and any order, okay? You can move, of course, those these two properties are only relevant to addition and also to multiplication, okay? But that's the idea of this any order, any grouping property with addition, okay? So this first part here, A, asks you to rewrite 5x plus 3x, these are two separate expressions, okay, and 5x minus 3x by combining like terms. Okay, so what they want you to do is they want you to write the original expressions and expand each term using addition. Ask you what are the new expressions equivalent to? Of course, these new expressions are going to be equivalent to the expressions we begin with. Okay, if they aren't, then we've done something wrong. So, what they're asking you to do here is something that's very kind of laborious in a sense. Some of you may understand this right away to how to combine these like terms, because these are both like terms. And again, this idea of a term. Okay, that definition we've talked about already. Each one of these, this 3x and this 5x, is a term, and the 5x and the negative 3x here is a term. They're both terms. Okay, so each one of these expressions has two terms. Okay, as we can see there. All right, so those each of those are a term, so two terms there. Okay, and you're combining like terms, and these are like terms because they both have x's after them. So 5x, it's a little bit messy here. 5x and 3x are both like terms in the sense that they are both a coefficient along with the x variable, okay? And 5x and the negative 3x are both have a coefficient and the x variable as well. So both of these expressions, and you are treating these as separate expressions here, okay? So if we work firstly with 5x plus 3x, If we were to expand each term using addition, okay, it would look like this. X plus X plus X plus X plus X. Okay, so this is this first one, this 5x. Okay, you see them there. 1, 2, 3, 4, 5 x's. And then plus x plus x plus x. This is our 3x right there, this one here. 1, 2, 3 x's, all right? If you add all those up, 1, 2, 3, 4, 5, 6, 7, 8, all of that equals 8x, okay? 8x. So this expression here, this really ridiculously long string of x's, is equivalent, of course, to that, okay, which is equivalent to that. So right here, what we've done is we have combined like terms. Easily enough would have been just to say 5x's plus 3x's equals 8x's, okay? But this kind of lets you see what you're doing, hopefully, all right? Now the 5x minus the 3x, again, similar, okay? It's a similar process. Now you have, so if we did 5x minus 3x, okay, we have, if we expand that out, we have x plus x plus x plus x plus x. Okay, here's that part. We have our 5x right here. And now if we're going to go ahead and remove 3 of those x's, okay, because we are taking them away via subtraction, okay, we are going to take away 3 of these. 3 x's there, okay, we are left with 2 x's, okay, these 2 x's here is what we're left with, okay. So therefore, if we combine like terms here, we are combining a 5x with a negative 3x, and if we combine those, we end up with 2 x's, okay, 2 x's. Okay, so we're going to apply this any order, any grouping property somewhat. I'm not going to do it the way they've suggested, though this doesn't pertain to you because you don't see this in your binder, but it just seems very convoluted, which means it takes too many steps, I think, the way they presented it. Hopefully, the way I present it will make some sense to you. But yeah, so B, so now what we're going to do something I haven't done before. We're actually going to find the sum of 2 expressions, okay? So we have one expression which is 2x plus 1, and then we have another expression which is 5x, and we are going to actually find the sum of those. Okay, we're going to find the sum of those. So I'm going to go ahead and go to another page here. Get a blank page. Okay, so here we go. We have 2x plus 1 and 5x. And I think some of you are looking at this and saying, wow, I know this. This is easy. Okay, and yeah, I hope that is the case for many of you. Okay, but for those of you who can't even fathom this idea of finding a sum of 2 expressions, well, listen, watch closely. Okay, you can write it this way, and this is probably the more traditional way to do it. So we have 2x plus 1. That's our first expression. Okay, and we can put that in parentheses if we'd like, plus 5x, because we are actually kind of separating those out. Now we could, the associative property is going to say we can put these parentheses anywhere. It doesn't matter where we had these parentheses, so we could, move it like 2x plus 1 plus 5x. This is what they had mentioned. okay, in their notes. But I just don't really see the sense of doing that. So, but just wanted you to know that that's the associative part of this, okay? But I'm going to just take that off. It just seemed to make sense to me. But I would like to reorder things, okay? And we've done this in the past, and I'd like to go ahead and use the commutative property, okay, and which means I can do any grouping, okay, not necessarily the order, but it does change the order. So what I want to do is I want to, actually we have done this in the past, and hopefully some of you remember this, but we could actually take this 5x, let's put it closer to that 2x, so we can go ahead and put 2x plus 5x, okay, and put those together, and then plus 1, okay, because now what we've done is we've combined, in a sense, well, we haven't combined them yet, but we've put these like terms right next to each other and kept this single number over here by itself, okay? So if we do combine like terms right now, we have 2x's and we have 5x's. Together that's going to give us 7x's plus 1, okay? So we have now created an equivalent expression right here. The 7x plus 1 is the same as this expression that we started out with, which was a combination of these two expressions, okay? So these two equal, in a sense, this right here, okay? So we've combined two expressions, and we've created one expression which has combined like terms, okay? We've combined the two x terms here into one single x term right there, 7x's, and of course we had to keep our 1 intact, okay? Now we can prove it, and we can prove it by looking at both of these expressions side by side, okay? So let's go ahead and do that. So if we take what we started off with, 2x plus 1 plus 5x, and right alongside of it, we look at 7x plus 1, okay? And what do we need to do here? Well, we need to find something to plug in for the x. Let's take, this could be any number at all. Let's keep it simple. Let's keep something that's really simple. Let's take 3, okay? So we are going to plug in 3 for our variable x. Therefore, we do 2 times 3 plus 1 plus 5 times 3, and then 7 times 3 plus 1, okay? Here we have 2 plus 3 is 6, 2 times 3 is 6, plus 1 is 7, okay, plus 5 times 3 is 15. We add those together, we get 22. And here you can see 7 times 3 is 21, plus 1 equals 22. So it does work. They are both equal to 22. Both expressions yield an answer of 22, or a solution of 22, when 3 is plugged in for the variable. Okay? So we've actually taken two expressions and we have found the sum of those. So we took these two expressions, found the sum, and this sum is going to yield the same answer, same solution as the combination of these two expressions. Okay, so here's letter C, and it asks you again to find the sum of negative 3a plus 2 and 5a minus 3, okay? Now keep in mind that we are attempting to use commutative and associative properties, okay? And that's this whole idea of any order, any group, okay? Associative property. We're trying to use these. So they only apply to addition and multiplication, okay? In this case, we're concerned with addition. So I want you to look very carefully, because if you notice this expression here, it is already in additive form, because hence the plus sign, okay, in the middle there. So this term is being added to this term. But if you notice, this 5a minus 3 is not written as a sum. It's not written as an addition expression. So that would be something you'd have to do first. And I think many of you, many of you know how to do that. And again, this goes back to probably the beginning of the second module, where we converted or changed a subtraction problem into an addition problem, which is, again, always a good thing to do. Okay, always. So make sure you do that first. So I want you to go ahead and pause. Try to do this problem by yourself, finding the sum of these two expressions. Okay, finding the sum of negative 3a plus 2 and 5a minus 3. Okay, so let's write our first combined expression. We would have, and again, let's use parentheses around both expressions. So we have negative 3a plus 2. No need to change that. We want to add that to 5a minus 3. Okay, that's our original two expressions combined into one expression. But now what we want to do is we want to use our additive inverse, so we can actually change that negative 3 right there. So the way we would write that then would be, this would stay the same here, this negative 3a plus 2 plus, then inside here we'd have a 5a plus our negative 3. Okay? All right, so this is these two expressions. So now we have it changed up. All right? Now, with any order, any grouping, let's go ahead and get these a's closer together, and let's get our the numbers, the 2 and the negative 3 together as well. So if we go ahead and do that, we can just go ahead and I wouldn't mind just going ahead and putting this negative 3a plus the 5a, put those in a parentheses together, and then plus, we have 2 plus a negative 3. Okay? All right, so we have those. So what we did, any order, any grouping, we have now just moved these around, get these together. Now if we combine our like terms now, over here we have our a's, we have a negative 3a plus a 5a is going to leave us with 2a, okay, because a negative 3 plus a 5 is a positive 2. That should be easy now, all right? And then if we combine these, a 2 plus a negative 3, of course, is going to yield us a negative 1, okay? So this would be our final sum of these two expressions, okay? You could, or you might have written it 2a plus negative 1. At this point, we don't need to do that because now we want an expression where we just have to just go ahead and plug in a number for a, okay? So, but, I mean, again, this is not wrong, okay? But this would be, in a sense, more right, more simplified at the end, okay? Okay, now with example 2, we're going to move into the realm of multiplication, okay? And again, it's this whole idea of this any order, any grouping, commutative and associative properties are going to apply as well to multiplication, okay? So instead of being asked to find the sum, we are now, because we're talking about multiplication, we're going to find the product of 2x and 3. Now 2x as one expression, 3 as another expression. Okay, so find the product of those. A couple of different ways to do this. We could use the distributive property. Okay, well, if we just wrote this out, it would look like what, 2x times 3 this way. We could use the associative property and just move things around, okay, and it might look a little bit easier if we did this, okay, because that's the exact same thing as this, as the first one looks like this, and now we have very easily, we could use our distributive property to figure this out, and then we just distribute there, and we have 3 times 2x is 6x, okay? You could also look at it as 2x plus 2x plus 2x, okay? Which is the same as multiplying 2x times 3. Add all those up, you get 6x, okay? So pretty simple in terms of finding the product in this case of 2x and 3, two very simple expressions, in a sense really two terms in this expression, okay? Okay, example 3 here, A and B, they ask you to use the any order, any grouping to write equivalent expressions, okay? And again, just to push this point, this any order, any grouping idea, believe me, this first one is easy because we kind of actually did it right here, didn't we? Same thing, okay? But if you were to do any order, any grouping, remember with associative property, we can move the parentheses around, so we could actually make it look like this. 3 times 2 times x, which equals, of course, 6, and then times x. Okay, again, x has to remain there. It can't do much other than just sit there. It's not going to change the value of x, okay? So that's what this idea of I used associative property to get to there. And down here I could do the same with 4y times 5. I could go ahead and move that. I could do 4 times 5 and then times y, which of course equals 20y. Okay? So, that is no more complicated than that. So, yeah, let's move on. Okay, let's continue on here with C. Again, using the associative property, we can go ahead and just put parentheses around the 4 and the 2, multiply those by the z, and that equals 8z. Pretty simple, okay? Because again, you're taking all of these and you're multiplying them by each other, okay? So, and again, if you notice, that one thing that's really important is that you see the variable is always going to be trailing, okay? It's always at the end, all right? It's never, I mean, the fact is that z8 is not the way we would ever express that expression or have that expression look, okay? Because the sense is we are plugging in a value for this. Now, whereas, I mean, if you plugged in a 4 for that z there, you would get 32. But if you plugged a 4 over here, you still get 32. But the way these expressions are to be represented or to look, to be expressed, is to have that variable as the trailing term. Okay? Okay, so let's look at D. D is a little bit different. You see we have two different variables. We have x in our first expression, and then we have our y over here. Okay. Now you can see these are two products. Okay. We have two products right here, and again we're not going to combine them. First of all, because they have different variables, and we do have that plus sign there. So if we take them apart, we see that we can do the first one. We can do 3 times 2. Looks very familiar, doesn't it? Times x, and then we have plus 4 times 5 y. Okay, so we have 6x plus 20y. Okay, and that's what we come up with there for that one. All right, and again, the reason we don't combine beyond this is because we have different terms. So these are unlike terms. This is here the variable is x. Here the variable is y. They have to stand separate of each other. Okay, they cannot be combined. Okay, now we have E. Takes it a step further. As you can see, they're kind of putting all these, a lot of these, just combining these all together here. So we have already done this first part. I guess we could just do it again. Remember we had 3 times 2x, and that's this right here, plus 4 times 5 y, and that's here. Just again, just moving things around. And then we have plus 4 times 2z. All right? And again, 6x plus 20y plus 8z. All right? And that's how we end. And that's what this looks like. That's what the combination of these is going to look like right there. We have just found the product of 3 different expressions, here, here, and here. Okay? And they exist right here. Okay? And again, these can be combined no further because they are different variables. So, we can't have 4 plugged in for the x, the y, and the z because they're all different. Okay? It's not going to happen because each of those variables being different, as these variables are different, the z and the y and the x, the fact that they are different means that they can never represent the same number to be plugged in. Okay? If they were going to be the same number, they would all be x's, or they would all be y's, or they would all be z's, and then we can combine those terms. Okay? But as it stands, this is as simple as we get right now, is that. Okay? Now F, of course, putting all this into a word problem, okay, all that we learn. So here we go saying, Alexander says that 3x plus 4y is equivalent to 3 times 4 plus x times y because of the any order, any grouping. Is he correct? Is Alexander correct? Why or why not? Okay, so I want you to think about that and actually maybe run a little proof if you want to, and plug some numbers in. Okay, and come on back. Well, Alexander is, of course, incorrect. Okay, now this any order, any grouping does apply to terms. Okay, it applies to terms. Now, if you notice, we have 2 terms here. Now, the way he has laid it out, he's made this into 1, 2, actually 3, 4 terms, or 3 terms in a sense. Okay, and you can't do that. Okay, you can't actually mess with things that way. Okay, so and again we could look at it and we could prove it. Okay, so if we have 3x plus 4y here, and then we have the 3 times 4 plus x times y, because that's what that means, x times y. Okay, you can see he's moved these, he's really messed with these terms big time. Okay, let's say we just said x equals 2, y equals 3. Okay, so if we plug in, so 3 times 2 plus 4 times 3, which is 6 plus 12, which equals 18. Okay, and then we do the same here. So we have 3 times 4 plus 2 times 3. Okay, so then we have 12, 3 times 4 plus 6, equals 18. Well, that was only lucky, okay, because All right, this is something to learn. Now, just because we did get the same answer here, okay, he got lucky because we are talking about this terms of how wonderfully associative and commutative multiplication and addition are. But if we go ahead and plug in a couple of different terms, a couple of different values for our variables, you're going to see how things will indeed change. So again, as that stood right there, yes, he did get quite lucky. So as 2 and 3, they do work out to be the same. But if we go ahead, you've got to remember now it has to apply in all ways, and a good way to check if you have done something right is to go ahead and use not just positive terms, but also negative terms, okay, or negative values. So let's say x equals -2 and y equals -3. Okay, so let's go ahead and do that. So we have 3 times a -2 plus 4 times a -3. So now we have -6 plus -12, and that equals -18. Okay. Now you know that there are some differences here when we're talking about negatives and positives and multiplying and adding. Okay, I know you understand that. So now we have 3 times 4, and now we are going to multiply -2 times not -3, but -2 times -3. Okay, and now you know that special nature of multiplying negative numbers. So now we have, again, 3, well actually, let's just do this. Let's do the multiplication here. 3 times 4 is 12, plus -2 times -3 is actually +6. Okay, and now we're going to get actually a solution of 18. So these are not the same. Okay, -18 is not equal to 18. So what Alexander has done, he's kind of, he's messed with these, and he's gotten lucky with one proof, and when he tries to prove it with positive numbers, okay, like we did with the 2 and the 3, it came out both 18. But now, when you try to prove it with negative numbers, okay, you can see, for example, and there'll be other ways this would fail as well. It fails here too, because this is 18, this is -18. They are not equivalent. Okay? And again, we'll see this come up again and again, and hopefully we'll understand it better and better. Okay, we have come to our lesson summary, and actually the page right before this, the lesson summary here, was your terms again, your relevant vocabulary. Hopefully you did watch that video on the relevant vocabulary before you did this lesson. If not, please do look at that. I kind of explain these in a little bit more detail. But keep this handy if you need to go back to it. Maybe bookmark it or put a little post-it note in this page so you can go back and maybe have this explained to you when you need to. Okay? But yeah, lesson summary here. So terms that contain exactly the same variable symbol can be combined by addition or subtraction because the variable represents the same number. Okay? That's why variable represents the same number. So, 2x plus 3x is the same as 6x, okay? Because we can combine those, right? Because they are the same number. I plug in 4 here and 4 for all these x's, and I get 8 plus 12. No, sorry, 8. Oh, this is not 6x. I'm sorry. Oh my gosh, guys, I'm stuck on my multiplication. That's 5x. So 2x plus 3x equals 5x. Yeah, I'm glad I did that. 8 plus 12 equals 20, and then 5 times 4 equals 20 as well. Okay, so they work out the same. Yeah, so these can be combined, and we say these are like. We call them like terms. This is going to be an expression you're going to hear a lot. Like terms can be combined. Okay. Now this idea of any order Any grouping can be used where terms are added or subtracted in order to group together like terms, okay? Changing the order of the terms in a sum does not affect the value of the expression for given values of the variables, okay? All right? And again, this applies in many ways to multiplication as well. And where we had subtraction, remember that we created a sum instead. If we had 2a minus 5, and we wanted to combine that with another expression, we could have, again, we do this, use the additive inverse to make it make it a sum or an addition situation. So we could then move this around wherever we wanted to. We could change its position. As this, we couldn't necessarily, because subtraction does not get commuted like addition does. Okay? So yeah, this was long, a little bit on the long side, this lesson. This is going to be the norm because this stuff deserves a lot of attention and is going to take us all some time to figure out. Okay?